even though we call this historical climate change, and I said it'll be Holocene, since we didn't touch on human evolution, and since climate change potentially could have played a big role in human evolution, we have to talk about it. So the best theory we have is that before the Pleistocene started about 2 million years ago, you had much flatter gradient, which is typically referred to as a permanent El Nino. Again, not everybody agrees with it, so Wikipedia will probably have other ideas. At least compared to today, where you have cold waters here, which is unfavorable for rainfall over East Africa, where you went from green forests to back to drier grasslands and savannas, is now preferred. So when El Nino happens and this water sloshes this way, we get much more rain over East Africa. So the idea is that if it was green and it became drier, then somehow it was a more permanent El Nino, and now we are into a more infrequent El Nino. Okay, so that's usually referred to as the Pliocene-Pleistocene paradox. Everything is a paradox. So over time, humans, I think just today in the papers, there is some new skull found in Greece, which says humans emigrated to Europe probably 210,000 years ago, which takes it further back than before. So new information will keep coming up, but those are kind of morphological fossil evidences which change the timeline a little bit. What doesn't change is the fact that if you take the genetic information, use the molecular clock and go back, we likely evolved in East Africa. This is unlikely to change. After we evolved, the question is, when did we emigrate out of Africa, and whether there were independent species evolving at the same time in different places, like China, or emigration into Europe, and so on and so forth. So this is a very nice diagram which looks complicated, but actually is very useful and has lots of information. So in colors, it's showing causes of, oh, I'm not in the display mode. So we are looking at essentially what kind of impacts humans and climate would have had on various species along the way. So this is the reddish magenta color is where humans are responsible. So there are ways to attribute the cause of extinctions to humans, or at least most likely. And wherever it's blue, it's mostly climate. And then where it is this other purplish color, darker color, you have not enough data to say what was the cause. So you can see different times when human beings arrived, but as I said, these numbers keep changing. So if you think about Europe here, you are more than 30 kilo years back, so more than 30,000 years ago for sure, because by then Neanderthals are always going extinct. What happened over 50 to 20 kilo years, number of provisional evidences you have for attributing extinction of megafauna, extinction of large animals, mammals, to one of these causes. And when it is green, the evidence is quite robust. And when it's the darker color, which you see here, it needs more work. In other words, the evidence is not sufficient. So obviously, sorry, I pointed to this already. This is the US, which got colonized much more recently by Europeans. As far as we know, humans have been here for a long time, and they have been here the longest time. So you can see that the number of megafauna that disappeared here is the smallest, even though the human beings have been there for the longest. And the human beings here have been probably the newest ones, and the evidence is quite strong that humans played a big role in causing extinctions with some contribution from climate, whereas here it was mostly the freezing and thawing, the ice ages and so on. So you have to basically try to understand then also South America, which is even later than here, Australia, also again the times change, estimates change as to when human beings got there compared to this, for example. So the migration that happened across here, it's not clear whether humans and megafauna crossed over together or just humans came and animals were already there, etc., etc. Nonetheless, you can see that the number of megafauna that went extinct, even though the evidence is not sufficient here, seems to have something to do with newer the arrival of humans, more the extinction of species. So maybe you can try to guess why that would be. Even human beings have been here the longest, but the number of species that disappeared is also the smallest. Right? They arrived here a little bit later, more species, a little bit later, more species, and so on. So why do you think human beings existed here for a long time, but still the number of species that disappeared is not as large as where they appeared in a new place?
They learn to coexist there, they adapted to the existing things, but when, as we in ecology study, if a new species arrives in a system, it sort of attacks and starves the other species of resources and is detrimental to the existing species. Maybe by that time, humans are also advanced enough to cause more destruction.
Right? So, Wikipedia or somewhere else? Or you just thought about it yourself? You read this or you just...
In ecology, it's similar to what we study.
Right? So if let's say people from West Bengal come to Bangalore, then a lot of Kannadigas will go extinct. Maybe. Right? So that is the general idea, that when humans co-evolved with species, many of these species are of course much older, but during the Pliocene, Pleistocene, the equid C3, C4 evolution, a lot of the grazers and so on evolved around the time, but there are many, many, many species that are much, much older. So the idea is that generally co-evolution favored coexistence and survival together, whereas when you went to a new place, you found new species. Either you got threatened or you wanted to taste them, so you started killing them, and if they taste good, then you kill more of them. Right?
So the idea of coexistence sounds like a very vague argument to me, because civilization can develop in a place which has less stress condition for, say, humans, as opposed to a place that has more stress conditions. So if I want to compare a place like India or Africa with Europe, Europe gets much more colder temperatures, there's much little resources. So when human civilization has to develop there and progress, it needs to extract more of nature to do so. But say in the heartland of Africa, where there's plenty of rainfall and vegetation and stuff like that, so you can come to a steady state where you do not need to extract as much, but have a sustainable lifestyle.
Yeah, so this points towards insufficient data, but your assumption that more harsher climate is not good for evolution or whatever you are.
It makes us more aggressive towards other species that might be fruitful to us for survival.
I mean, these are speculations. There's no fundamental principle there, right?
Also, another thing is possibly that later on during the migration, they were exposed to species which were more of a threat to them, like much larger mammals, and clearly they had to. And also, if you kill a mammoth, then it would feed the whole community for much longer.
Right, but the biggest elephants are still here, so it's not, and lions, tigers, whoever else. So it's not, all these are kind of speculations, as I said, but fundamentally speaking, more environmental niches happen when the climate is more variable. Actually, you get more species, and colder conditions, metabolic rates go down, and people live longer, and you get less sick because there are no much far fewer diseases, and so on. In the tropics, temperature favors lots of microbes, viruses, bacteria, and water spreads it. So if you have diseases, you will have many more deaths, infant mortality, shorter lifespan, and so on and so forth. So biology is not that obvious in terms of relation between environmental changes and who survives and who does better. If you remember Darwin, he always said it's not the smartest, it's not the strongest, it's the most adaptable, right? So potentially you would have adapted more there than here. Okay, you would have invented more. So it's a question of whether it's invention or killing others to survive. So it really depends. So if people live in igloos at high latitudes still and they catch whales or seals and so on and so forth. So the story is a bit complicated, but there is pretty good evidence to say that the number of extinctions here is much smaller than here, here, and here, for example. So that is kind of the explanation. Plus, as you arrived later, you probably had more and more inventions, even though there is evidence that already things were being invented in Africa before they moved out, and so on and so forth. So the spears and the ability to throw is one of the big things that made us better killers in many ways. You have a question?
Yes. I had mammoth extincted because the ice is got over. They were suitable for cold climates, not the warm one. I mean, is this picture presenting mammoths or elephants?
Mm-hmm. Are you talking from the movie or from a book? So mammoths lived in Siberia. They disappeared in South America or North America only about maybe 5,000 years ago. So it's not entirely clear. The rate of change matters, as we'll see later on that it's cold species and warm species. If things change rapidly, then many don't survive. But if things change slowly, then many can survive and adapt, and so on and so forth.
So have no species been driven to extinction in the Indian subcontinent?
There's no data, basically, not much data from there. So India is not very big on paleontology and so on. There are few that focus on birds and so on, and there is some evidence that dinosaur fossils were found in, I think, Gujarat or somewhere. So Madhya Pradesh and so on. So there are not enough data to say anything. So how have things changed? Coming back to the Holocene, we'll go back to the human evolution a little bit later on, I hope, because I didn't explain what caused this. Essentially, we mentioned it, that the New Guinea, Australia were far south of the equator during this time. This doesn't show it properly. This is showing modern continents. So you had a very different circulation here than we have now. Once you blocked this pathway, then you increased the zonal contrast. So the east-west temperature gradient changed, and if you use your fundamental knowledge, then you know that cold temperature means high atmospheric pressure, sea level pressure. Warm temperatures means low sea level pressure. And on the equator or near the equator, where you have Coriolis going to zero or very small, you know that such a pressure gradient can drive a very strong zonal wind, right? Doesn't get deflected too much because Coriolis is small. So you have a very strong zonal wind. So you have southeast trades, northeast trades, but on the equator, because of this strong 8 to 10 degree temperature gradient, you also have strong zonal winds. And if you know about El Nino already, then you know that that's what changes quite a bit during El Nino. Okay, so this is kind of the things that people like Bill Ruddiman always talk about, that human impact started already many thousand years ago. So this is basically showing a long-term composite of glacial, deglacial changes in carbon dioxide and methane. And the blue line and the blue curves are the range of changes we have seen for many previous glacial, deglacial changes. And the red or magenta lines here are basically showing the changes for the current deglacial period that we are looking at. And the point is that as soon as agriculture began to expand from the so-called Fertile Crescent or the Leviathan around the Tigris River and so on, you can see that CO2 began to increase, and we went out of the envelope of glacial, deglacial scales in both methane and methane is later than CO2. Lot to do with deglaciation, but also with rice paddies and livestock and other water bodies. Once you start collecting big water bodies, especially behind dams, you collect a lot of sediments and you have a lot of methane emissions from these stagnant water bodies. Okay, so the spread of the Fertile Crescent, so around this region here into everywhere. So it started around 13,000 years ago, so right after the deglaciation, right around the Israel, Syria, Lebanon, Jordan, those kind of Iraq, the Tigris River and Turkey and so on, and slowly expanded with modern times all the way into Europe. And we don't have a similar figure for China or India, but here it is showing much later arrival of agriculture as such. So you can see that this is showing 7,000 to 5,000 years, but this is saying much later, like maybe 5,000 onwards. So we believe we are the oldest culture, obviously, and then there are some people here who believe they are also the oldest culture, but whatever little evidence we have, we know that these people will always say they are also older than everybody else, right? So there is plenty of evidence to say that agriculture most definitely evolved around here, and North Africa was also much wetter, as we saw already a little bit. So you can put that in the context of the temperature change. We will look at a couple of such figures. The main point you would want to make in this context, going back to the long time scale temperature change we saw, is that Cretaceous was very warm, 15 degrees warmer in the Arctic than present. So global warming is very small compared to that. And if you go back to several billion years ago, it was even warmer than that, 21 degrees warmer than present. So the idea is that the modern human being that has evolved over this last 10,000 years has not seen a very big temperature jump. Changes have been only about half a degree or so, and each one has had some impact on the human civilizations that existed at the time, whereas we are now way beyond the scale of change we have seen in our history, right? So we came out of the Ice Age, we had a hiccup, the so-called Younger Dryas, and we jumped into this Holocene optimum. The name is not really very meaningful, it's just something that can correspond to increased monsoon over Africa and evolution of agriculture and so on and so forth. And you can see that this scale is quite nonlinear here. So you have various periods like Mesopotamia flourished when we came out of the Younger Dryas, let's say, and then medieval warm period came along. Again, each one is relatable to orbital forcing plus other internal feedbacks just coming out of the glaciation and so on. So Greenland had melted away quite a bit. Agriculture was possible on Greenland, so Vikings made it all the way, and Vikings in fact even made it all the way to North America. There is plenty of evidence that Eric the Red Son, Leif Erikson, made it all the way to Nova Scotia, northern Canada, even before, several centuries before Christopher Columbus set foot on the Western Hemisphere. Little Ice Age, we will look at details of these things. So the medieval warm period ended, and then there was quite a bit of cooling, which we will see was related to volcanic eruptions and sunspots. And this was not global. It's called Little Ice Age. Definitely lots of evidence that Europe had extensive freezing, crop failures, and so on and so forth. And Industrial Revolution came right along there. So we cannot explain fully why the Little Ice Age ended, other than to look at sunspots and volcanic activity. But one of the ideas is that the beginning of the Industrial Revolution and the coal burning put a lot of carbon into the ice that had built up over Europe and in the Alps and so on, which accelerated the melting, and then you got into this Industrial Revolution. We'll see more details that the temperature change is never uniform, especially when you look here. We'll have lots of ups and downs, what we call internal variabilities. And the projections are important basically because we have to understand how much warmer we will get and what it will mean, not just in terms of glacier melting and sea level rise, etc., but also extreme events, hurricanes, typhoons, cyclones, whatever, plus what happens to agriculture, what happens to positive feedbacks in the system, and so on and so forth. So when we look at the projections, it will not be so much about the exact number, but it is to understand the complexity of making such projections. How many things you have to actually worry about, right? As Yogi Berra said, prediction is very important, very difficult, especially when it's about the future, right? So if you want to make predictions using astrology, it's easier, but if you want to make actual predictions of the future, then it will not be that easy. So you have to put that in that context. So you have had huge swings if you go to the beginning of the Cambrian, massive swings, and PETM, as we said, stands as a unique example of where very, very rapid warming happened. But it turns out that this warming rate is much slower than what we are doing here. As far as we can estimate from the data we have, the warming rates we are experiencing, let's say since about the 1980, 79-80 period, is quite a bit faster than what happened here. So the point again is, when you look at past changes, first thing to remember that modern human beings didn't really exist before this. There were other species here which ran around, did hunting, gathering, Neanderthals, Denisovans, Floriensis, all kinds of species. We started somewhere here, and we are basically evolved to be what we are in this period, where the change is remarkably small compared to this, but we are now kicking up massive changes. So the question is not whether planet will go anywhere, it's not going anywhere. Whether life will disappear, it will never disappear because life has survived everything. Only question is, what happens to Bengalis, right? So if you look again briefly at the civilizations that existed before about 8500 BCE, what is called Common Era. People don't like AD and BC that much, so the new terminology, politically correct, is Common Era. So everybody was concentrated on the Nile. Water is always very important. Where civilizations evolve is always around water. And we know that the monsoon humidity and the monsoon peaked, the greening of Sahara happened around that period. So the civilizations spread out from the Nile all over. Lots of lakes had much more water, especially Lake Chad and so on. And that lasted for several thousand years, so let's say 2,000-3,000 years. Slowly, monsoon began to dry up again, so all the civilizations started to move back towards the Nile River. This evidence is fairly clear that civilizations did grow and fill up lots of Africa, and then they came back. So the ethnic groups or whatever cultures, tribes that still live in very, very dry regions like the Bedouins or the the Kalaharis and so on. There are even some hunter-gatherer tribes left in Africa and so on. So they have obviously survived. So again, it's a question of whether the life completely disappears or some still survives and manage to live through it. So pretty much anywhere you go, people disappear, but some survive. Like the Vikings disappeared, but there are still tribes living on Greenland. People still live on Greenland, not completely disappeared. Okay? So just to look at our own story, we also had the annual monsoon versus the summer monsoon, and you can see that probably in some times of the past, if summer monsoon was very small, probably there was a different winter monsoon. So the annual rainfall was quite large, 1,000 millimeters or more is massive amount of rain. But both of them kind of dropped off during this period where we know that the Harappans and Mohenjo-daro kind of disappeared, right? So definitely climate is a stressor. But as I said, what happens is when the rainfall is good, they expand, and especially in terms of agriculture and the way they use water and so on, becomes quite, I don't know, careless or whatever. But there is evidence that as monsoon began to weaken from there to there were many efforts made to build structures to save water, harvest water, channel water, transport water, etc., etc. That's also true for places like Hampi and so on, or other kingdoms that empires that worked more recently in the last let's say last 1,000 years, last millennium. So human beings expand very quickly. They try to innovate when bad times come, but eventually, depending on how hard or how tough the drought is. So floods are never a problem. Droughts, which can last for a long time, are always an issue.
So this data is from several places in India or
this is more focused on these diamonds here. Yeah, it is much more from that period. In fact, not much has been done. The Chinese are running some good models to understand the past Holocene timescale rainfall change over China. In India, such modeling is not yet caught up, but if there is people who are interested, you can use their simulations to look more specifically at what's happening here in terms of orbital forcing versus human impact. So the question is, how did human impact amplify the natural change? That's always a question, yeah.
Does it also coincide with the Aryan invasion theory that time?
Why not? I mean, the Aryan is not still, whether Aryans were all just from here or they were really from Germany, we don't know, right? It depends on whether you ask Hitler or somebody else. But in general, there have been invasions here. When did Alexander invade?
2000, more than 2,500, 2,300 years.
Right? So some 300 BC or something, let's say. So that is kind of getting into that period. So the question is not who invaded when, but how our climate changes relate. So if Greece was also having issues, either they have a lot of resources and they become adventurous to see what is there, or they become resource limited and they go looking for resources. So if this dried up here, it's likely that this is not such a local thing, right? Because a lot of circulation here is from the Mediterranean. So it's likely that Mediterranean was also having huge disturbances. This is going into that period. So all this drying up started it was most likely a global phenomenon. So in that sense, people, whether it's Genghis Khan coming down 17 times or Alexander coming once or twice, or Indians going into this direction with Buddhism and so on, it's always about two things. One, you have a lot of money and you want to invest somewhere else, or you are run out of food and money and you start invading the neighbors, right? That's what it is. But there are books which talk about the connection between climate and civilizations. Peter Lamb, I think, has, this is now a bit old, but there are other books which talk about history and climate. But if you talk to anthropologists, they will tell you that climate scientists typically take like this and then correlate and say, haha, that did that. But anthropologists say that's not that simple. And it's clear that climate is one of the stressors. There are other things happening already that kind of amplify.
So if you could compare the Indus Valley civilization with the Nile Valley, so somewhat similar that there was a drying period, some sort of climate perturbation for which, but in the Nile region we have had continuous human civilization existing since the day it started. But here is a break.
Yeah, there is a break. Well, as we said, we don't have data. So when we looked here, this is showing from 13,000 years, whereas this is now going down to 7,000 years, right?
Yes, so if there was a climatic, if there was a perturbation and the monsoons receded for a couple of years, even then we'll still have water in this river because it's a glacier-fed river, right? Glaciers will not go, the Himalayan glaciers will not go extinct that quickly.
Wow,
so
this is
similarly, like Nile was being fed by Lake Victoria. So even if I have less rainfall in an area, like you mentioned that the humans back then had the technology to store water, come up with ponds and stuff like that.
First of all, monsoon doesn't disappear for a couple of years. This is a couple of 100 years. Okay, so.
Same thing is happening in Nile. People are not disappearing.
Huh?
Same thing happened in the Nile, right?
No, the same thing happened in Nile. All these civilizations now are based on technologies. This is going back to this time. This time, those civilizations disappeared and they came back to the Nile. Because Nile.
Survive along the Nile, they could survive.
Yeah, because there was still water. I mean, remember, this is a desert, so you still have East African monsoon and the Blue Nile that is feeding this and Lake Victoria. So you have ITCZ coming here. I don't know if you remember the ITCZ. It's the Sahara that's bone dry right now. But other places, they still have grasslands, savannas, so there is rain. So there are lakes, Turkana, Tanganyika, and Victoria. There are many lakes, Kenya, and so on. They have had Ethiopia. They have had civilizations for a long time, right?
So similarly, like Indus should also be able to support, because there is no evidence of the Indus drying up. There is just evidence of river migration and lack of monsoon.
It doesn't matter whether they moved and merged with the other populations or they disappeared. The point is that this civilization boomed and there were cities with very heavy populations and they all kind of went extinct. So we are not saying they all dropped dead, right? So they moved, as there were invasions, they were mixing. So genetically, people look at it. So there are some that are much older than others. There is a lot of mixing happening in the north compared to the south and so on and so forth. And you have immigration also here. There is Chinese influence from this side. There is Indians going this way, right? From 7th, 12th, I don't know, whatever centuries Buddhism and Hinduism went. Bali has Hinduism from the 11th century. So people moved all the time. But despite that, these people, if you remember, everybody probably came out of Africa at some point. The question is, when is the biggest emigration happened out of Africa? And then when did the rest of the Eurasian continent get populated? Okay.
So we stick to that theory that there's one single point of population and not simultaneous development.
No. So genetic technique is very good. So that tells you that we inherit most of our genes from East Africa. Then the question is other species that evolved along the way, and this, now we have only Homo sapiens. We carry some Neanderthal genes, but in between you had Homo habilis, Homo erectus, Floriensis, Denisovans. Everybody appeared and disappeared. The question is, did they evolve independently, or they, were inbreeding related, whatever. So anyway, that's just kind of more of evolutionary biology and so on rather than climate. Nonetheless, out of Africa, emigration theory is good, and there is a paper last year, I think, by Axel Timmerman that argues climate change drove the biggest emigration around 50,000 years ago because of climate. That was in the middle of the last ice age. So again, these are kind of fitting the story rather than saying exactly what happened, right? So this is the Viking story. So they colonized all kinds of places. Here is the Gulf Stream and the North Atlantic Drift going in both directions. So they occupied, you can see the numbers here, starting in 800, 860, 870, they colonized these places. Do you see any number there? They were here till the medieval warming disappeared, and they made it all the way into northern Canada. So there's evidence that the Vikings had made it here. So when the refreezing started, medieval warming ended, then everybody went back. So this is still basically frozen, but there are still people living there, right? They didn't. So obviously they have Viking blood in them. It's not like Vikings disappeared. It's just that Vikings disappeared from Greenland. They probably mixed with the other tribes that live there. So now you have, all these are related, the Scandinavians, Danes, and Icelanders, and all are basically related to each other, right? So in South America also you have these stories of Wari Empire, Tiwanaku, and much more recently you have Incas and Mayas and so on. So in the last millennium. And here there are periods where you had, so this place would get rain when? During an El Nino or during a non-El Nino?
During a
Sure. He's saying.
it's warmer.
Hmm?
Because it's warmer, then other times it is cold desert, then it is not anything.
Right? He's saying you are reversing it. Why?
El Nino is when this part is cold, right?
So that's
Sorry.
what
El Nino is when the warm passage.
you should have the picture of the globe in your mind always, with temperatures, monsoon circulation, trade winds, westerlies. That's a very simple thing to remember. So you just stare at that global map for 10 minutes and then you should never forget it again. So this gets rain during El Nino. So which means if you don't get an El Nino for a long time, right, then you're going to have very, very dry period. So here also, if you go to Machu Picchu and so on, there are water harvesting structures, fog harvesting structures. The tribes that live there now can predict El Nino based on how humidity is changing and so on and so forth. So they also try to survive dry periods, but many of them went extinct or became much smaller in number or whatever. Only after the Columbian period, they started colonizing. The Spaniards colonized extensively this region and so on. So again, the peak monsoon around 9,000 to let's say 6,000 years was very much related to the increasing precessional summer insolation that we talked about. And then the summer insolation has been dropping since about 6,000 years ago. That's consistent with the precession cycle. We expect 23,000 years. So at some point after the medieval warm period happened, the temperature started to drop, which refroze Greenland. So that is one key event that we talk about, the disappearance of Vikings. But over Europe, especially Netherlands and so on, you have lots of evidence of war, famines, all all sorts of things that is related to the so-called Little Ice Age. So that basically followed the end of medieval warm period. Black Death, the plague, and so on, the Manchu conquest of China, rise of potatoes. So these kind of things are related to lack of resources. Cold temperatures, agriculture dying, then you start attacking the neighbors looking for stuff. Potato was not original to Europe, came from South America, as Sankalp says, and the French Revolution. Again, these are historically, you just try to weave through the story. That is the artistic presentation part. Things like Frankenstein, Dracula, and so on are related more specifically to this. The year without summer, so you're talking louder than her now. So she was trying to say something, right? You said, what were you trying to say? The what? He heard you and said it loudly. So there was a big volcanic eruption, and it basically put so much aerosols that the entire year became colder by half a degree or more. And that's where they made a bet, and they took a vacation and sat down and wrote scary stories or whatever. Invention of bicycle, year without summer, and so on. So people have been looking up PDFs or something, or Wikipedia, whatever. So this is the Icelandic sea ice extent going back to the millennium. And you can see that the medieval warm period was beginning to end, and there was a spike in volcanic activity around this time. And then there are a series of sunspot minima that we will look at that basically cooled the temperature, at least in the northern hemisphere. There is no big evidence that this cooling was very significant in terms of glaciation in North America or other parts of the globe. So Alps and Northern Europe were definitely feeling the pinch in terms of frozen canals in the Netherlands and so on and so forth. So the forcing here is much more related to internal feedbacks of volcanoes and external forcing from sunspots. Okay, what do sunspots do?
If they increase, it's hotter.
It is hotter. We will talk in terms of energy, right?
More influx.
So if basically they are like knots in the magnetic field or whatever, whenever there are sunspots, around that there is a much brighter region called plage, which is French word for the beach, looks like a beach, I suppose. So every time you have a sunspot, actually the net amount of energy coming from the sun goes up. So that's what you have to remember. You'd think more dark spots means less energy, but actually it's exactly the opposite. More the sunspots, more the energy. So there is evidence, for example, here it's the same picture, you cannot clearly see, but this church is still there. This is from 1997 and this is from 1896, about 100 years apart. The Argenteri Glacier had come all the way down to this church, and they prayed to the Lord and the glacier went back. No, actually no. The ice age, little ice age came to an end. So the question again asked here is whether this was related to internal feedbacks or was it related to industrial revolution. For example, if you had a lot of coal burning starting from this period, then you would put a lot of pollution and carbon on the glaciers, which would accelerate, which would reduce the albedo and accelerate the melting. Nonetheless, by 1997, we are already well into greenhouse effects and increased CO2 and so on and so forth. What do volcanoes do? Typically, you don't look at just one volcano. What you do is you take many, many volcanoes together and you look at the concentrations before the volcanic eruptions happened and after. So you start with when the volcanic eruption hadn't happened yet and look at few years. So you increase the sulfate aerosols in the stratosphere quite significantly, and you cause significant cooling because of these sulfate aerosols, which are very bright, and they scatter radiation, incoming radiation. So essentially they increase atmospheric albedo. And why do we worry about whether it's in the stratosphere or troposphere?
Stratosphere not will be escape soon.
It will not be?
It will be escape.
It won't be rained out, right? So it will stay there for much longer time. So the residence time of stuff you put in the stratosphere is much longer than if you put it in the troposphere. In the troposphere, this thing becomes acid rain, H2SO4, and fall out fairly quickly. Residence time would be much shorter than if you put it in the stratosphere. The other thing that happened is if you looked at the volcanic explosion and solar radiation, you can see that the volcanic activity was much lower than into the 12th and 13th century. Okay, so there was an explosion of volcanic activity, and now in the 20th, 21st century, it's again reached somewhat of a minimum. You hear of volcanic eruptions here and there, but not all the time, right? So volcanic eruption has a natural variability of how many volcanoes are going off, how many are active, and so on and so forth. Not very easy to predict, not clear there is a real periodicity or anything. So this is something like white noise or red noise that we were talking about, that this one has a very specific time scale, whereas this one seems more random, right? But nonetheless, if you started to put aerosols into the stratosphere and began to cool, then ice albedo feedback can take over and create something like a little ice age, even though you have to explain why it happened mostly over Europe and not elsewhere, right? That's not fully explained in terms of circulations, but people do model simulations, and the models are able to reproduce the last glacial maximum or the little ice age and things like that. Of course, then you have to give the models also the volcanic forcing. So this is the sunspots. You can see, even though it's a sunspot, it looks much, much brighter than the rest of the sun. And during this last millennium, you had Oort minimum, Wolf minimum, Sporer, Maunder minimum, and so on, which means every time there was a minimum, there was a reduction in incoming solar radiation. So there were multiple minima along the way, which means radiation got reduced. So you are adding volcanic forcing and also reducing energy coming from the sun. Together, they created this little ice age. Okay, so this is also seen in terms of measured in terms of C14 production. As we said, C14 depends on the energy coming from galactic cosmic rays. So depending on solar activity, those rays can be changed. So amount of energy that can produce C14 from nitrogen also changes with solar radiation. Okay.
So if the flux of energy escaping the sun is more during sunspots, then is it not uniform? That why are they getting reflected away from Earth when sunspots are high?
Why are they getting reflected away from?
Yeah, it's saying since cosmic rays are getting reflected away from Earth, they are not able to produce enough C14.
Yeah. So
The source is increasing its production of rays, then there seems to be some selectivity that will not go through Earth or pass by Earth to,
yeah. So Earth's magnetic field, and there is energy coming in, and then there is Earth's magnetic field. So the cosmic rays are interacting with Earth's magnetic. So you are all, for example, aurora borealis, right? So their activity depends on solar flares, various other things. So sun is not just sending energy. Sun is also sending out a lot of other crap. Maybe it's useful, right? Space weather, this, that, other things. So the cosmic rays are always coming towards Earth. Whether they can make it to the Earth's atmosphere or not depends on Sun's activity.
Was the magnetic field changing during that time?
Yeah, these are knots in the magnetic field.
In the Earth's magnetic field.
No, we are talking about solar magnetic field, not Earth's magnetic.
And Earth can deflect. Earth's magnetic field is the
I didn't.
that can deflect charges from the sun. So if we have more of those rays and Earth is able to deflect them away, so maybe our magnetic field is
What is so? You are bringing too many things. Earth's magnetic field is not changing at this time. What is changing is sun. So then we are only worried about what sun's energy and magnetic field are doing to the cosmic rays.
If it's increasing, why is it not that they are coming to the Earth more? If it's producing more of cosmic rays.
More galactic cosmic rays are deflected away from the sun. So, What is the question? This is just saying that if you have higher sunspots, then you will have more plages. Okay, then you will get that means there is a stronger magnetic field coming from the sun. This is going to deflect the cosmic rays that are coming towards Earth. Is that clear? These are galactic cosmic rays. Who said they are sun's cosmic? Yes. So there are many, many words, and then there is one word here, which is somehow getting blocked by the sunspot or the sun's magnetic energy. Right? So the problem is when you heard something and you are carrying that information and you insist on using it, you tend to ignore what is obviously sitting there. Right? So it is galactic cosmic rays that bombard nitrogen and produce C14. But those cosmic rays depend on what the sun is doing. More can come in or less can come in. That's all it is saying. Okay? All right. So this is the opposite. Here it is saying that we had minimum sunspots and minimum radiation, which means you had reduced solar magnetic field, so you had more C14 being produced. So you can see that C14 is increasing over this time. Very simple things. Just track them. Don't get confused or don't.
Is there some average over the globe of C14?
Yeah, C14 is considered well mixed and it's produced everywhere. So there is no strong.
We are measuring it from the atmosphere, from troposphere. We are taking sediments in.
No. In the past, obviously, you didn't have measurements from the atmosphere. So you will have to look in some proxy tree rings or sediments or ice cores or somewhere else. So, okay.
So all different sources of C14 measurements are represented. It's not just one particular source.
Yeah, this will be combination of all the proxies you have. But now there are also models which can tell you how C14 production changes with solar activity.
If there's a lower C14 production, we have a higher delta 14C, high atmosphere.
When sunspots decrease, what should happen?
Sunspots are decreasing, then we have lesser cosmic rays coming, so less production of C14.
Okay. Don't try to, again, as I said, don't try to go back to the information you have. Use the information you have to. I'm saying when there are more plages and more stronger magnetic field, then that deflects cosmic rays. That would reduce C14 production. But here we are having fewer sunspots, fewer radiation, weaker magnetic field, which means more cosmic rays, which means more C14. It's very simple.
more C14 is more delta C14C.
Well, delta C14 because you are comparing it to some standard. You are never saying C14 is 18%. You are always saying how much it's changing with respect to some standard. Okay? All right, so this is now coming more towards the modern period. So you're looking at O18 signals from ice cores in 4 regions, and you can see that over time the Greenland glacier grew into the Little Ice Age. Tibet had more glaciation, Peru had more glaciation. Antarctica is not so clear because, as we said, doesn't necessarily always get synchronized. Plus, Little Ice Age was mostly a northern hemisphere phenomenon and maybe much more so the European, but you can see that there is some also Asian and South American signature. So this is Andes going up in altitude, but at lower altitude on Antarctica, you don't have that signature. So there is some, because you can change this by changing Pacific circulation, for example, right? Whereas you need to change Southern Ocean to change over here. So obviously it's not global in that sense. So along the way, we are also changing winds. We have looked at ocean currents before. This is just showing it in more detail. All you have to remember again is that you have northeast trades, southeast trades, and there are some details here as to what actually happens. There are things like equatorial countercurrent, which we haven't talked about, but considering the difficulty we are having with sunspots, we will not worry about this right now. Okay, so nonetheless, you have this large-scale gyre here. You can see that it's much more focused here than here, but there is a huge seasonality. If you remember the expansion and shrinking of the subtropical high and the subpolar low and so on, you know that there is a strong seasonality. Plus, this is much different configuration than this. So you can see that this gyre is very different than this gyre, which is split into 2 pieces. And this gyre is different. This, now you can see much more clearly why the Gulf Stream has much more of an impact here than the Kuroshio. Kuroshio is going up and it's mostly recirculating and getting split into pieces. So there is a North Atlantic current and a North Atlantic drift. It's called Gulf Stream here, but by the time it gets to here, it's called North Atlantic current, and then it becomes the North Atlantic drift. And you have, so just like there is a Kuroshio, which is a warm western boundary current going north from the tropics, you have a cold western boundary current coming. So this will be counterclockwise. This is clockwise. So you have to remember this is trade winds versus westerlies, whereas this is westerlies versus easterlies. So you have different circulation here. So you have, this is called the Oceanic current, this is called the Labrador current, and in the subtropics you have the California current, which is bringing the cold water, the Peru Humboldt current here, Benguela current here, and here you have a Canary current coming down, and so on and so forth. Okay, so Indian Ocean is obviously very different because of the changing seasonality of monsoonal circulation, but Indian Ocean also has a southern subtropical gyre because you have southeasterlies here and what winds are here? Easterlies? It's the same. It's the same, right? So you have trades, westerlies, westerlies, easterlies, easterlies. It's the same. The strength will be different because land, ocean, etc., etc. So this Southern Ocean, we said, is different because it's like a channel. The question here is how much energy can the wind put into the ocean? This is now important because of global warming and renewable energy and so on and so forth. For example, if monsoonal circulation is changing with global warming, how is it changing and so on. So you can also see that westerlies would probably put much less energy here because it's a much smaller ocean than here. So if you go to surf in the ocean, you'll get much better surf and waves on this side than on this side. Okay? or even on this side. So typically here, the percentage of energy from the winds into the ocean is only about 2 to 5%. That's because of the fetch and the duration of the winds and so on. Whereas here it will be much higher, maybe 20, 30%, and the winds will keep on churning the ocean, and eventually the Ekman currents hit the bottom, and there is something called a J-bar effect, joint effect of baroclinicity and bottom relief, which becomes a limiting factor for how much more energy can go into the ocean and so on and so forth. So people make maps of wind energy now because, let's say, Tamil Nadu is, I think, already invested a lot in offshore energy farms and so on, or even on land when you put windmills and so on. If global warming is changing wind strength, then you want to be careful, because if you want to invest $1 billion in building a huge offshore wind farm, and then in 10 years the winds die down, then it can be a problem. So people are thinking of building floating farms so you can actually move them if the winds change and so on and so forth. But you know that on land, they're building these huge, massive structures everywhere, which obviously may or may not have wind energy in a few years. Okay? So this gives you a good sense of where Labrador Current and Greenland Current, etc., are bringing in cold water. Gulf Stream is bringing in warm water. So you have the so-called Gin seas here, Greenland, Iceland, Norwegian seas, and Labrador Sea, which are producing your deep waters. Antarctica is complicated. Basically, we will see later on again that you have the Antarctic circumpolar current, which is going from west to east. So it's making this loop, and it's meeting the subtropical gyres at this end. Within that, it has these Ross Sea gyre and the Weddell Sea gyre and so on. That's where you form some of the heaviest Antarctic bottom water and Antarctic deep water and so on and so forth. And this provides you the polar front. So the data here, for example, you cannot even go there during winter time. There are permanent camps on ice which collect data in the atmosphere and so on, but ocean data is heavily limited because you can only go there during the summertime. Okay, but this is showing the much more complicated story that we mentioned several times before. So if you have continent here, the glacier is flowing. This is called the ice stream, right? And we said it's anchored somewhere, and then it floats on the ocean as shelf ice. That's different than sea ice because this is glacier that has flown onto the ocean, right? So that's formation is different, its properties are different and so on. So if you warm the ocean, right, if you change the Antarctic circumpolar current and you're having lots of heat, the first thing to remember is if wind-driven currents can go much deeper in the Southern Ocean because of the channel configuration, then the heating will also penetrate much deeper in the Antarctic. Okay? So Antarctic is warming, but it is where the heat can go down to the bottom very quickly because you have these strong currents that are taking it down. And where is that water going? That water is going into the Indian Ocean and the Pacific Ocean. So Indian Ocean is also warming very, very rapidly, as we will see later on. So the question then is, how much of the Southern Ocean warming is coming into the Indian Ocean, and how is that affecting the rate of Indian Ocean warming? How long it takes for this water to invade the Indian Ocean and so on.
But this is through thermohaline circulation?
Well, this is part of the thermohaline circulation, but we are now, this is all local circulation, right?
Yes, in the Antarctic context, the deep water formation is happening.
Yeah, so there is deep water, Antarctic bottom water here, there is Antarctic intermediate water here, and the North Atlantic deep water, which is heavier, is under the intermediate water and coming up. So this is...
being carried from Antarctic Ocean to Indian Ocean is what we read is that happens very soon, over 1,000-year time scales.
Well, the entire circuit is 1,000 years.
But still a couple of years.
Well, it's probably like more like 50 years. Indian Ocean is very small, right? So entire thing, if you start from North Atlantic and go to the North Pacific and come back, that is hundreds of years. But Indian Ocean getting Southern Ocean water and back, that doesn't have to be that long, okay? So as you warm the Southern Ocean, these shelf ice pieces are getting carved, which means they are breaking into pieces, iceberg carving. So when the Titanic hit an iceberg, basically those are icebergs formed off of Greenland. So whenever icebergs flow onto the ocean and ocean is warm enough, big chunk will be taken off. So every few years you will read that a big iceberg broke off and it's floating around, and eventually it'll melt, of course. So the warm ocean can accelerate the iceberg carving, not melting, it's iceberg carving, breaking the iceberg shelf ice into pieces. When that happens, you change this dynamic. So the iceberg here then kind of jerks forward and the grounding line changes, and all kinds of processes happen because of this piece breaking off here. You also have things like polynya, which means it's a big hole in the sea ice or glacier. And what happens, the sea ice or a glacier is essentially like an insulator. It has high albedo, it will prevent the ocean from losing the energy. Whereas if a little polynya opens, that's going to lose 1,000 times more heat than under the ice. So you can begin to lose enormous amount of heat from the ocean to the atmosphere and create all kinds of circulation changes and so on and so forth. So the point I want to make is that compared to the Arctic, which is a much simpler system of sea ice, where you are almost monotonically melting sea ice and summer ice disappearing or becoming smaller and smaller, Antarctica is complicated because of these processes, plus the fact that the warm ocean is going to warm the atmosphere, which will increase the humidity and is in fact increasing snowfall in some parts of Antarctica. So we'll see later on that Antarctic ice glacier is not melting uniformly, but it's melting in some places and actually accumulating mass in some other places. Okay, so this is again looking at other evidence of the Little Ice Age and global warming. This is showing corals stacked. Basically means there are not a single coral may not live for so long, but you take multiple corals and calibrate them and stack them together. And you can see that there are warm temperatures. The Little Ice Age came, and you can see clearly these blue minima where the minimum temperature was much lower than the medieval warming. And then we have climbed now by this time into global warming. So corals are basically forming these skeletons of calcium carbonate, and the crystal structure depends on temperature. So corals are sensitive to salinity and temperature, hence sea level change or acidification and so on and so forth. We'll look a little bit more at acidification once we get into modern climate change, but you can imagine everybody has an intuitive sense of what acidification is, or you have read Wikipedia, right? What is acidification? No? Okay. I thought somebody would have read already.
Is it like decreasing the pH level?
Yes? How does it happen?
So oxides of sulfur and nitrogen dissolve in water and decrease the pH.
Huh? Oxides of sulfur and nitrogen. Carbon.
Carbon dioxide.
We're talking about global warming, so obviously CO2 is highly soluble in water. CO2 plus H2O gives H2CO3, carbonic acid. But ocean chemistry is a bit more complicated. It doesn't remain H2CO3, it splits into carbonates, bicarbonates, so we'll have to look at that. So let's touch a little bit on global warming, El Nino, because we cannot do actually even global warming without understanding El Nino a bit better. I'm sure now there are few people who think they already know El Nino very well. Huh? Who knows? Sankalp, right? What is your name? Huh? Bibash. B-I-B. B-I-B-H-A-S. What? Bibash. Anybody heard this name before? You made it up or it's real? Huh? You're some alias you are attending here. What is your real name?
That's my name.
You know El Nino? Who wants to come here and explain El Nino briefly? No? What's your name? Huh? Avantika. You know El Nino, right? Yes.
In 2013, I read a news for it, like, because that time this monsoon was delayed, but not clear enough to explain.
Who knows El Nino? Okay. So then we will learn it. So this is the normal condition, which means what? So who can explain this quickly? What are we showing here? This was not in that news article. So we have northeast trades and southeast trades, and we have Ekman spiral. What happened to Ekman spiral paper? Did you bring it? Did you show it to Bibash? You are supposed to show it to Bibash and discuss. Ekman divergence. So when you try to push water from east to west, Coriolis is going to push to the right and push to the left. So you have Ekman divergence. So you have cold water coming up. Sea surface temperature is cold and there is upwelling, which means what is this thermocline? Thermocline is pulled up, okay? So that water is, even though it's diverging, there is plenty of it moving west. It's going to pile up and create deeper thermocline and warm water. So this is the basic configuration or climatology or normal condition. So there is a seasonality, of course, as the ITCZ moves back and forth, trade winds get stronger and weaker, upwelling is maximum in July, August, September, and weaker in March, April, May, and so on and so forth. But nonetheless, you have cold temperatures, high sea level pressure, warm temperatures, low sea level pressure. So you have, in addition to the trade winds, you also have strong zonal winds or east-west winds. Where there is warm water, you have rising air, condensation and heating and rainfall. So as I said here, there's about 5 meters of rain. So you can imagine how much heating that is. This essentially drives global weather and climate in many ways. So when this moves around, you know that it's going to drag around the entire global circulation, which is why you have changes in monsoon and South American rain, South African rain, and US rain, and so on, and African rain, and so on and so forth. Okay? So Darwin is somewhere here. Warm temperatures means low pressure. Tahiti is somewhere here. Cold temperatures means high pressure. So once in a while, for reasons that we don't completely understand, even though there are a million papers and Wikipedia articles, we don't know exactly why the system sloshes back and forth, but from a mathematical sense, you have essentially the trade winds, the atmosphere has no boundaries. Winds can climb the mountain and come down on the other side, whereas ocean has boundaries. So if you put boundaries in the ocean, you're going to pile up water here and you're going to pull up water here. So as the water is pulled up here constantly, the atmosphere is trying to heat it constantly. There's 100 and some watts per meter squared of heat being put in here all the time. And much less heat, zero heat being put in here, maybe a little bit being lost to the atmosphere from the ocean and so on. So this is almost like something that is with a rubber band, it's being held this way. And then once in a while it lets go and then the system sloshes, right? So it's almost like some fundamental zonal mode of variability that exists. It could be just because this is a very non-linear thing, right? atmospheric heating and convection are very nonlinear exponential dependence of humidity on temperature, and then when this energy is released, it's got time scales of hours to days to weeks, and you can obviously slosh it a little bit, and if you move it a little bit and start some feedback or start a wave, you have waves that can go along here and push the thermocline down or pull the thermocline up, and you can start all kinds of feedbacks, right? So that's essentially what happens during an El Nino. Whatever little feedback starts, the trade winds get weaker, the thermocline gets deeper here and shallower here, so the entire thing becomes much flatter. So you can see that it's deeper here and shallower here, but now it's much flatter. The warm water has spilled all the way. So even though this color is not very obvious, we'll see that the warmest water begins to move in this direction, so becomes anomalously cold here. So the convection weakens, so the rainfall here begins to decrease a lot, and it increases a lot here. So you get mudslides, storms, and heavy rain on this side, and you get droughts, dust storms, and so on this side. What should happen? Right? So if you have, so you can now think of your positive feedback. Here, you have strong winds causing upwelling, high pressure, low pressure. That's going to create winds that way, and that will make upwelling even stronger. But somehow if you weaken these winds and weaken the upwelling and make it warmer, then the pressure will become less, and the pressure gradient will become less, winds will become weaker. You can see anomalous currents and winds. So the upwelling become even lesser. So you have again a positive feedback. Positive feedback in the one direction and then positive feedback in the other direction. So Gilbert Walker had speculated that this pressure oscillation is related to Indian monsoon droughts and famines. Only in the 1960s, 1963 to 69, Jakob Bjerknes showed that this kind of a feedback exists, and that is related to El Nino. So it's the first time that people realize that El Nino is the same as what Walker had called southern oscillation. There's an echo here. So what is southern oscillation called in Kerala? Is there any Malayali here? 3 of them. I better be careful. What is it called in Kerala? Don't know? Huh? Southwest. It's called southern oscillation. So what happens? So that is El Nino, right? So trade winds weaken, upwelling weakens, zonal winds weaken, and you slosh the whole system this way. You move the rain system, you will create global, what are called teleconnections, which I will show in a minute. And sometimes the opposite happens, where the trade winds get stronger than normal, and the thermocline will get shallower than normal. The cold waters extend, they get colder and they extend further. If you, this is the normal. If you compare that to La Nina, so they get stronger, so coastal winds are stronger, the cold tongue extends further west, this gets warmer and gets squished, so you get more rain here and drier climate here. So this is the reason why California and these regions, La Paz all the way down here, these are all dry regions. This is why if you go here in summer, you will feel very cold. There is a story that Mark Twain said this, but there is no evidence that he did. He said, the coldest winter I experienced was a summer in San Francisco. So it gets pretty cold here. So we haven't talked about biology yet because we haven't looked at the profiles of carbon dioxide and so on. But everybody knows that where there is upwelling and cold waters, you will get rich nutrients and Something. High productivity, so you'll get more phytoplankton and more zooplankton and more fish and more biodiversity. So Galapagos, which is sitting here, is a hotspot for biodiversity, right? So you have El Nino, you have normal conditions, and you have La Nina. Why is this important for global warming?
If it is warming everything, the contrast may decrease, and which is why we may not have El Nino or La Nina.
So why is it important for global warming?
If it is, there is no upwelling and no biodiversity.
And global warming.
Oxygen is released less.
And what happens to the heat?
It is, so the coldness will be decreased.
And
Therefore, it will be hotter.
Affects the global circulation. So if global warming happens, then there will be less heat distribution.
just look at this. We are saying ocean brings up cold water and atmosphere soaks it up with a lot of heat. Right? So ocean's heat uptake is determined by how much cold water is coming up here. Okay. If global warming is happening,
Increase in seawater temperature will eventually.
the question is whether global warming will warm more here or the same. Because if you warm here and you reduce the sea surface temperature gradient and the pressure gradient, then you will have a positive feedback, right? You can reduce the pressure gradient, weaken the winds, further reduce the upwelling, which means more of El Nino.
Because the warm water is spreading.
This is the normal condition, right? So the question is, under global warming, normal condition will look colder here and warmer here, or warmer here and colder here, or same amount of warming. So amount of ocean heat uptake will be determined by how global warming will affect this region. If this warms faster or as fast as here, then you can weaken the gradient, weaken the winds, weaken the upwelling, and eventually the ability of the ocean to take up heat will keep decreasing, because unless you bring up cold water, you cannot take up the heat. Okay? Right? So that is called ocean dynamic thermostat, which means if global warming somehow cools this region, then you can increase the winds and then you can increase the upwelling and you can create more and more heat uptake by the ocean. So global warming, which is what we call as atmospheric warming, will be modulated by this region. But if on the other hand, this warms faster than here, then you will reduce the gradient, you will reduce the winds, you will reduce the upwelling, and slowly you will begin to reduce the amount of heat taken up by the ocean, and you will accelerate global warming. So this region is very critical because this is a dynamically driven region which is soaking up lots of heat. Okay? So we watch very carefully how this region responds to global warming. Okay?
How exactly does the oscillation is forced? I mean, if I have a spring, there is this restoring force which is bringing it back and pulling it. What exactly is reducing, bringing the thermocline below and then driving it down?
So finally, Sankalp has asked a brilliant question. We said there is a positive feedback. We said warm water moves, winds weaken, upwelling weakens, that weakens the winds further, so we have a positive feedback going on. Now he's saying, how will it stop?
Or how is the warmer things coming here in the first place? Like
What
the
do you
beginning.
What do you think?
Is there an exact reason, or normal circulation somehow has some time period and
No, you can look at it, there's an exact reason. You are collecting heat during this phase or during the La Nina phase. You are soaking up heat, you are moving it here, and you are collecting. You are exhausting it here. Once you spill it, it's like a bucket of warm water. You take a bath and it's gone.
so what is causing the spilling? Is it there is some threshold heat that it can have after that you spill, or
What did I say? What did I say?
you need more water?
Huh? I said for reasons we don't exactly know, every few years the system sloshes. And I said because you have such a zonal contrast, you can build mathematical models which show that it automatically goes back and forth. You build it up and then it spills and then rebuilds, it spills. It's called a recharge oscillator, recharge discharge oscillator, which basically says that given the trade winds and this contrast, there is a scale of this circulation which keeps on accumulating warm water, and at some point it spills it. But this is a consistency check. It doesn't explain the periodicity. Either it's a periodic system, in which case the period should be constant, but it's not. Or it's not an oscillator, in which case somebody has to kick it, and we don't know what exactly kicks it. So we don't know whether it's an unstable oscillator or a stable, delayed, decaying, damped oscillator. So there are theories. Basically, you can always watch El Niños happen and then you say, oh, there were waves, this happened, that happened. So every time, it's like monsoon. Every monsoon looks different, and every monsoon, Sulochana Gadgir will write a paper about it. But we have not made any fundamental progress. Right? So there are those fundamental questions remain. Yeah.
So two doubts about the El Nino years. If the trade winds are weakening, which means precipitation at the ITC should also weaken.
ITCZ moves, yeah.
So whatever precipitation is happening along the western coast of South America, shouldn't that, because of the entire feedback mechanism, also reduce?
Yeah, so we are, this ITCZ is somewhere here. So this is cold water, this is cold water. We are not showing something here, right? That is the ITCZ.
During the early years.
Yeah, so ITCZ has to move south.
But we are still having precipitation there, right? So what is causing that precipitation?
It's causing precipitation. You are causing precipitation. This is drier, but you will cause precipitation there. This is drier, you will cause precipitation there. This is wetter. ITCZ moves south, which means you will create dry conditions there.
So when we say that during El Nino years, most of Peru and all, they have precipitation.
Warm, cold. You're increasing precipitation here, increasing here, reducing there. Because ITCZ has, remember, ITCZ is here, now ITCZ is kind of moved. So
Why particularly there's no wind converging there, right? The Galapagos area that you were mentioning.
Galapagos is here, I'm pointing to there.
Yeah, there.
There is no winds there.
What exactly is converging? Like, is it a local circulation or is it the
So
trades?
it's always convergence of winds, always, because that's what brings moisture.
Are these the two trades or some local?
There are mountains, so trades are coming this way, and there is a ITCZ going all the way here, right? So there is convergence all along. Okay, so, and remember, this is also very warm water here. So for ITCZ, we need warm water, right? So question is, why does ITCZ go all the way up here? And one argument is because there is so much warm water here. But there is also mountains here and gap. Those are kind of details which I don't think you need to worry about. Just understand large scale features, and then once you are very comfortable with those, then you can get into details. Okay, so we have gone a few minutes over, but we can come back and meet if there are questions.